Hello and welcome to this lesson on polynomial functions. Before you've analyzed different graphs of functions, and now in this lesson what we're going to be doing is graphing polynomial functions and also modeling real data to fit those polynomial functions. So the first example we're going to look at is graphing the function f of x equals x minus 3 all taken to the fifth power. So if you remember from previous lessons, even functions like y equals x squared would make a parabola like this, whereas odd functions such as y equals x cubed, which are symmetric to the origin, tend to increase quickly and then near zero still increase but not as much, and then kind of increase at a faster rate once you get beyond the fractions near zero. So these are kind of the general shape for functions of the even variety and the odd variety. Now notice, since this function is taken to the fifth power, this function is more likely going to match the odd function over here rather than the even function to the left. So if you also remember, we determined how this minus 3 would affect the function as well. Since we're subtracting the 3 inside the function, that's going to cause our function to move to the right. Remember, subtraction inside the function means moving to the right, and subtraction outside the function means moving down. So basically what that's going to do is it's going to give us a similar function to y equals x to the third, since they're both odd powers. And the only difference is it's going to be moved over to the right 3 units. So you're also going to have a slightly steeper function than x to the third, since it is taken to the fifth power. And it should look something like this. I probably didn't draw it that well, so what I'm going to do is bring up the calculator and we'll type in y equals x minus 3 to the fifth power, and take a look at our graph. Zoom out a little bit. And as you can see, it looks kind of like we predicted. It's moved over 3 units, and it looks similar to an x to the third graph. Now let's look at a second example where we want to graph f of x equals x to the sixth minus 1. Notice this time the minus 1 is outside of the function rather than inside the parentheses, like the minus 3 was in the previous example. So what that means for us is that this is going to move the function up and down. And remember, outside the function, negative values mean that the function will be moved down. The other thing we want to take notice of is that in this case we have an even power to the sixth, so this is more likely to look like a parabola rather than the earlier odd function we had in the first example. So we have a parabola that's moved down 1, so it's going to be down here. The other thing about this function is that the parabola will be more extreme because it's taken to the sixth power rather than the second power, so those values are going to increase much faster than your general x to the squared parabola. So if we take a look at that on the calculator over here, you can see it's a little flatter on the bottom than I drew it, but it does increase rather quickly, and it's a parabola moved down 1 unit. So at this point, go ahead and pause the video while you figure out the answer to this question, and then go ahead and answer it on Edpuzzle. You should have determined that in this case the answer should be B. Don't let the fact that the 2 is in front fool you. You're still adding 2 to the x cubed function. So that's going to move it up 2 units, and you're going to have that similar shape that we learned that x cubed takes. So now what I want to do is I want to look at this graphic from your textbook and kind of analyze it a little bit. What it is the leading term test for polynomial end behavior, And what we're looking at is the general polynomial, as you can see here, the f of x equals some constant times x to some power. And you're going to have as many constants as you have power. So for instance, if this was x to the third, you would have a constant here. You would have something times x to the third plus something times x to the second. Eventually, plus something times x to the first power plus something times x to the 0th power, essentially, which is 1. So that last term where you have technically x to the 0th power is just going to be a constant value. So we'll look into these a little bit more in the next couple examples so that you can be more familiar with what a polynomial function looks like. But for the general case here, let's assume that n, in other words, your highest power in the polynomial function, let's assume that that's odd, and also that your first coefficient is positive here. So if that's the case, then as you go to the left, you can see the limit of your function goes down to negative infinity, and as you go all the way to the right, you see your function goes to positive infinity. And you're going to have some kind of direction change here in the middle. As you can see over here, if your highest power is odd, so you have something like x to the 5th or x cubed or x to the 7th, and also this first coefficient is negative, what's going to happen is your limit as you go to the left is actually going to approach positive infinity, and then you have some directional changes in between. But in the end, as you go to the right, you're going down to negative infinity now. And these functions will change, but the basic end behavior, remember, that's what we're looking for here. The end behavior is going to stay the same. So the last two cases where you've got an even function where your highest power is even. If a is positive, both to the left and to the right, your function is going to go up to infinity. However, on the other hand, if your leading coefficient is negative, both ends of the function are going to go down to negative infinity. So let's apply that knowledge to example 3 here. Describe the end behavior of the graph of f of x equals 3x to the 4th minus x cubed plus x squared plus x minus 1 using limits, and then explain your reasoning using that leading term test that we just talked about. So this looks like kind of a crazy function that you wouldn't be able to analyze very much, but based on our leading term test that we just talked about, our leading coefficient is 3, so our leading coefficient is positive. And the other thing we want to look at is the highest power, which is even. So those tell us two things. The even power tells us that the two ends are going to go in the same direction, like a parabola. The positive coefficient tells us which direction those two ends of the function are going to go, and that is going to be positive since it's a positive 3. So how we can write that is as our x approaches negative infinity, as x goes to the left, my function will equal positive infinity. And the same thing goes for when my function goes to the right, to infinity. My function is going to reach infinity that way as well. So that's my end behavior for this function. Both directions we're going to reach infinity, and as you can see, when I graph this function, that's what happens. As we go to the left, the function approaches infinity, and as we go to the right, the function also approaches infinity. Alright, so let's look at another example of this where we have the function f of x equals negative 3x squared plus 2x to the 5th minus x to the 3rd power. Now don't be fooled by this one, because it's tempting to say, okay, we looked at 3x to the fourth in the last one, let's go ahead and look at negative 3x squared in this one. But the problem with this function is they gave it to us out of order. As you notice, the highest power is actually this 2x to the fifth, and it does include every power after that, because if we wrote this as 2x to the fifth, you might say there's no x to the fourth power to continue going down by one power. But really, even though we don't need to write it, you can kind of imagine that x to the fourth power having a coefficient of 0, so that's why it's not there. And then x to the third has a -1 coefficient. X to the squared has a -3 coefficient. And then there really is no x to the first power or a constant value at the end. But you can see each power of x is still represented. It's just that there is no coefficient for some of those. So we only need to worry about 2x to the fifth minus x to the third minus 3x squared. And to determine the end behavior, we really only need to worry about this one with the highest power of x, the 2x to the fifth. So as you can see, the 5 is an odd number, so we're going to have a function looking something like that. And we also know that the left is going to be doing the opposite of the right because it's an odd function. The other thing we know is that the 2 is positive, so we know that it will look something like this, where as we go to the left, we end up in negative infinity, and as we go to the right, we end up at positive infinity. So how we can write that is the limit as x approaches negative infinity is negative infinity, and the limit, or I should have said f of x. And the limit as x goes to positive infinity of f of x is positive infinity. So that's my end behavior of this function. Notice that all we needed was the highest power of x to figure that out. Alright, let's look at one last example here of this type, determining the end behavior, and then I'll have you try one on your own. F of x equals negative 2x to the fifth minus 1. This one's easy to see which one has the highest power, the x to the fifth there. So because my power is odd, I know that the two ends are going to be doing opposite things. And because my coefficient is negative, it's going to be opposite of our previous example. Remember, to the left it went down, to the right it went up. Now in this case, as we go to the left, my limit as x approaches negative infinity, now instead of going down, the graph's going to go up to positive infinity. And as we move to the right, as x goes to positive infinity, what my function is going to do is it's going to go down to negative infinity. So if we look at that on the calculator, as you can see, that's what happens as we move to the left. We go to positive infinity, and as we go to the right, we go to the negative infinity. And that should be what you expect, because your typical x to the fifth function is going to look like the chair we talked about, where it goes up and then up some more. Whereas if you flip it by making the leading coefficient negative, you're going to just flip it upside down, so you have the opposite sort of effect. Alright, so go ahead and pause the video here and figure this out. The reason you want to pause is because you'll miss out on the question if you don't pause to think about it. And in a minute I'll show you the answer. Hopefully you chose the answer C, because as you can see, the highest power there is x to the fifth. Since that's odd, notice your end behavior is opposite, so that eliminates answers A and B. And then we look at the leading coefficient, the -3, and since that is negative, what you're going to see is Going to the left, you're going up, and going to the right, you're going down to negative infinity. Alright, so this might be a good point to pause for the day and try some of the homework problems. Otherwise, if you'd like to keep going forward in the video, that's fine too. Now we're going to be talking about how to look at the polynomial in terms of its zeros and its turning points. And as you can see in this graphic, how to determine the number of zeros is by looking at the highest power, the 6 here. What that tells us is at most there are 6 distinct zeros in the graph, and what we then do is we take 1 minus that highest power, which would be 5. That tells us how many turning points we could have. So this function, 3x to the 6th minus 10x to the 4th minus 15x squared, is graphed over to the right. As you can see, there are no more than 6 times it crosses the x-axis. There's actually only, it looks like 3 zeros here. And what we decided was there's a maximum of 5 times it can turn around. It looks like it turns around 1, 2, 3 times. So it's got 3 zeros and 3 turning points. What we're going to do in the next couple examples is determine, our maximum number of zeros we can have and our maximum number of turning points we can have, and then figure out how many of each the graph actually has. So looking at example 5, state the number of possible real zeros and turning points of this function f of x equals x cubed plus 5x squared plus 4x. Once again, what we're going to do is we're going to find that highest power, x to the 3rd. So that tells me that at most I can have 3 zeros, and then if we take 1 less than that, which is 2, that means I can have up to 2 turning points. So the next thing that it tells us to do is actually to determine those real zeros by factoring. So what we're going to do is we're going to figure out x cubed plus 5x squared plus 4x. We want to know where that function is equal to 0, and we can factor this out. So first of all, you can see that there's an x term in common in all of them. So let's get that out of the way. So we're left with x squared plus 5x plus 4 equals 0. And then the next thing we want to do is we notice that we have this trinomial, and we should be used to factoring those by finding the two numbers that will both multiply to give us 4 and add to give us 5. Hopefully you can see that those numbers are 4 and 1, but don't be fooled into thinking those are your zeros. Remember, we have to factor those out. So x plus 1, x plus 4 equals 0. So what it actually ends up being is my zeros can either be -4, -1, or 0, because we want to find numbers that will make each of these factors equal to 0. So those are my 3 zeros at 0, -1, and -4, and we can check that on the calculator. As you can see, the function does appear to cross the x-axis at 0, over here at -4, and over here at -1. So go ahead and test your knowledge here and see if you can figure out the answer to this question. Now, in that previous example we looked at, you might have remembered that that is called a quadratic function because we have this specific type of polynomial expression called quadratic form, where the function is written as a times some variable or expression u squared plus b times that same expression to the first power plus a constant, where a, b, and c are real numbers and u is some expression in x form. So an example of this is if we look at that function below, x to the fourth power minus 5x squared minus 14, what we would consider that quadratic form, because if we call the u expression x squared, the first term is x squared squared, which is x to the fourth, and then in the second term we have what we called u, which as you can see u is x squared. So we have that x squared squared, we have x squared left alone, and we have a constant. So let's go ahead and take a look at some examples of that. Alright, so in example 6 here, we've got state the number of possible real zeros and turning points for h of x equals x to the fourth minus 4x squared plus 3, and then determine all of the real zeros by factoring. So if you recall, we use the highest power, x to the fourth, to determine that we have 4 possibilities for zeros. The maximum number of zeros we can have is 4, and one less than that, we could also have 3 turning points. So let's actually figure out those zeros. And remember the quadratic form, we don't necessarily have to have x squared, x, and a constant. We can have x to the fourth, x squared, and a constant. If we call u our x squared, what we can then do is we can substitute u in for x to the fourth. So x to the fourth is really x squared squared. So we could say u squared. And then since x squared is u, we can say minus 4u, because I'm just putting in u for every x squared. And then obviously 3 would just stay the same. So you can see I put u squared in for x to the fourth because that's x squared squared. So now we can factor this out. We can set this equal to 0 and factor it out just like we would any other quadratic function. It looks like my two numbers that would add to -4 and also multiply to -3 would be a -3 and a -1. So those are the numbers we're going to put with u. So that makes u either equal to +3 or u is equal to +1. The thing is, that tells us that u is 3 and u is 1. It doesn't tell us what x is. So we have to remember that u equals x squared. So that means that x squared is either going to equal 3 or x squared is going to equal 1. So when we remember, each root is going to have 2 possible factors. So when we take the square root, x is going to equal plus or minus the square root of 3, or x is going to equal plus or minus the square root of 1. That's 4 factors, or 4 zeros. So the possibilities are that x is going to equal plus positive radical 3, negative radical 3, positive square root of 1, which is 1, or the negative square root of 1, which is -1. So those are my 4 zeros that we can find for this function. Alright, so this one's probably a little more difficult because you have to do one more step in order to get to that quartic function, as we would call in the previous example, where you have the x to the fourth and the x squared. You can get to that form, but there's, like I said, there's one more thing you have to do. Go ahead and see if you can solve this one and figure out the zeros. Now, one other thing we want to look at is if you have something which is known as a repeated zero. What if you were to factor something out and you got 2 factors that were both x minus 1? You would then have a repeated factor of x equals 1. In the same way, we're going to have a repeated factor here, a repeated 0. And what that means is if you have a repeated 0, say you have it twice or any even number of times, that means that your graph is actually touching 0. It doesn't actually cross unless you have an odd number of factors. So let's just look at that, what I'm talking about in this example, where we have x to the fourth plus 5x cubed plus 6x squared. Determine the possible zeros. Again, we could have 4 zeros and therefore 3 turning points. And we also want to determine those zeros. So we're going to set the function x to the fourth plus 5x cubed plus 6x squared equal to 0. And in this case, we can take out actually an x squared from each term. And we're going to be left with x squared plus 5x plus 6 equals 0. Now we have a quadratic form here that we can factor. So we've got x squared, and my two numbers look like they're going to be, let's see, 2 and 3. So x plus 2 and x plus 3 would give me that quadratic function. So that means my x can either equal 0 if x squared is 0, my x can equal -2 if x plus 2 is 0, and my x can equal -3 if x plus 3 is my factor that's 0. So those are the three real zeros I came up with. But if you remember, I said anytime you have kind of a repeated factor, because really we've got, you can think of this as x times x plus 2 times x plus 3, and it's either this x or this x could equal 0. So that's why you really have two zeros at x equals 0. And what you'll see happen in the graph is when you have two factors like that that could equal the same thing, what could happen in your graph is that instead of crossing the x-axis, it's going to come down and just sort of touch it. And we'll take a look at the graph real quick so you can see what I'm talking about. Notice that, like we determined, at -2, you've got a 0. At -3, you've got a 0. But at 0, you don't quite cross the axis. You have that repeated 0 there because of this squared. You don't quite cross the x-axis. It just touches its tangent to the x-axis. So go ahead and try another one of these, similar to the last example, only in this case you are going to have a repeated factor. Now this definition kind of summarizes what I was saying earlier, how if you have more than one of the same factor, for instance, if you have x minus c taken to some power, and you're setting that equal to 0, you would have a 0 at c, because when you solve for x, that factor becomes 0 when x equals c. So if this occurs an odd number of times, then the graph is going to cross the axis. Like you're used to seeing just like x minus 3 not taken to a power. So if you just had x minus 3 equals 0, you know that the graph crosses the x-axis at x equals 3. However, if you were to have a repeat of that 0, for instance, if you had the quantity x minus 3 squared, then you know that it's not going to cross the x-axis because you have an even power. It's just going to be tangent to the x-axis like we saw in the earlier graph. Alright, so in this last example, what we're going to do is kind of apply all that we know so far to figure out what this polynomial is going to look like. Now, for f of x equals x times 3x plus 1, times x minus 2 squared, the first thing we want to do is apply the leading term test. So how we're going to do that is we're going to take each factor, the highest power of each factor. So the first factor of x, we're going to take x. We're going to take that times 3x, and then whatever power is out here is what we're going to take 3x to. Since there's just 3x plus 1 to the first power, we're just going to leave it 3x. Now notice my highest term here is x, but it's taken to the second power. So I'm also going to multiply by x, but I'm going to take that to the second power. So when I look at each factor, my leading terms end up being x times 3x times x squared. So when I combine all three of those terms, I'm going to get 3 times x to the fourth power, and that's eventually what's going to tell me what the end behavior of my graph does. So remember, since I have an even number here, my end behavior is going to do the same thing as I go from to negative infinity and also positive infinity. So since it's even and I have a positive coefficient, remember what that means is as x goes to negative infinity to the left, and also as x goes to positive infinity to the right, my function for both of those is going to go up to positive infinity. The second thing that they're going to ask us to do is determine the zeros of this function and then state the multiplicity of any repeated zeros, meaning do any of those factors appear twice. So obviously we have here x could equal 0. If we set this function equal to 0, 3x plus 1 times x minus 2 squared. If we set that function equal to 0, x, of course, could equal 0. 3x plus 1 could equal 0. And we have two possibilities of x minus 2 equaling 0, because that term is squared. So then we have, obviously, x equals 0. For this one, we need to solve. So we get 3x equals negative 1. Divide both sides by 3. We get x could equal negative 1/3. And for both of these over here, if we add 2 to both sides, we're going to end up with x equals 2. We kind of get that factor twice. So if you remember, because we get that 2 factor twice, that means that the graph isn't going to cross at x equals 2. Essentially, it's going to be tangent to the x-axis at x equals 2. So finally, the last thing they're going to want us to do with this type of function is graph it. As you can see here, I just quickly rewrote the function and kind of set up an interval of each point where the graph is going to cross the x-axis, so each 0. So we know the graph will cross the x-axis at negative 1/3. We know it'll cross the x-axis at 0. We know it'll cross the x-axis at 2, or at least be tangent to the x-axis at 2. So what we want to do is for each of these intervals, we've got negative infinity way out here. We've got positive infinity way out here. In each of these intervals on my graph, I'm going to want to figure out a point in that interval. So let's deal with numbers that are easy to work with. From negative infinity to negative 1/3, the easiest number to deal with is probably negative 1. From negative 1/3 to 0, negative 0.1 is probably the best we're going to be able to do. Maybe negative 0.5, but it's your choice. You just need to pick an x between these intervals. From 0 to 2, obviously 1 is probably the easiest to work with. And from 2 to infinity, let's just pick 3. Notice I never picked any number that was actually a 0 on the interval. I only pick numbers in between. So let's make an f of x chart here. So for those x's that I found, we have -1, negative 0.1, 1, and 3. When I put, and you can just use your calculator to figure this out, but when I put -1 times 3 times -1 plus 1 times -1 minus 2 squared, what I'm going to get for that is 18, because -1 minus 2 is -3. Square it, you get 9. 3 times -1 is -3, plus 1 is -2, and then we're also multiplying that by -1. So -1 times -2 is +2, times 9 is 18. So then, real quickly, if I put -0.1 in my calculator, what I should get out is -0.3087 rounded. If I put 1 in, I should get 4. And if I put 3 in, I should get 30. So now I essentially have a lot of points to deal with when I'm graphing it. I know that my zeros occur at, we've got -1/3 will give me a value of 0. 0 is going to give me a value of 0, and 2 is going to give me a value of 0. I also know that we'll have points at -1, 18, -0.1, -0.3 roughly, 1 and 4, and then 3 and 30. So when I look at my graph, I can start graphing these things. Let's see, let's go by maybe 2's here. So if I have -1/3 on my x-axis, if this is 2, the -1/3 would be maybe here. I'll have a point. Let me use a different color. Go with red. I'll have a point at about here. At 0, 0, I'll have a point, and at 2, 0, I'll have a point. So then I also have a point at 1, and then we'll go up here to about 4. I have a point at -1, and then way up at 18. So somewhere up here. I have a point at -0.1 and -0.3. So we know it does kind of dip below the x-axis there. And then also at 3, which about right here, and way up at 30, something we can't really see. So just a rough sketch of my graph based on those points, maybe something like this. We know it's tangent at 2, so kind of like this weird W looking graph. Let's go ahead and take a look at the actual graph to see how close we got. So as you can see on the calculator, we didn't do too bad. So go ahead and see if you can try this on your own, determining the zeros and stating the multiplicity of this function. Alright, so we're finally going to look at our last example here. As you can see, we've got a table showing a town's population over 8 years. Year 1 referring to the year 2001. Often a nice way to simplify what we're looking at is not to graph the year 2001, but just call it 1, and 2002, and so on. So what we're going to do first, we want to create a scatter plot of this data, and then determine the type of polynomial function that could be used to represent it. So how we're going to scatter plot this into our calculator is we want to go into our stat and go to edit, which is your first option there. And I've got a bunch of data in here that I'm going to clear out by going up to the name of the list and hitting clear, and we'll just clear everything out. And what you're going to do now is for L1, we'll put our year data in, so just go 1, 2, and so on, and I'll fill this out in a bit. And then for population, you just kind of put in that into L2, so put 50-50 and 55-10, and keep going down your list until you have both of those filled out. So as you can see, I just went ahead and filled in the rest of the number of this town's population. And now what I'm going to do is I'm going to go ahead and, first of all, let's go into our y equals, make sure everything's cleared out. I'm also going to hit second y equals, which is my stat plot, and you should make sure that your plot 1 is turned on, but let's make sure that our x list is L1. I'm going to make sure my y list is L2 instead of L3. So if I just go second 2, that makes my y list L2. Make sure it's turned on. Make sure the type of plot is this first one here, the scatter plot. So when I go and I go back to second stat plot, it's on. If I go to zoom and I go into zoom stat, which is number 9, so basically you can just click zoom 9. That will give you a scatter plot of our data, which looks like a polynomial function. The next thing we're going to want to do is actually fit that function to a particular type. So what we can do is we can fit this to a function. If we go to stat and then calc, you can see there's all sorts of different options here. You have a linear regression, which would be if your graph was in the shape of a line. Quadratic, if we had a quadratic function like a parabola. Ours seems to be more, cubic because it's changing directions. So let's go ahead and try that one. So if we go to cubic reg there, and if you go ahead and put in second L1, comma, second L2, and hit enter, what that'll do is it'll give you some coefficients for a cubic function. So how you could write that is you could say 10.02 x cubed minus 176.3 x squared plus 807 x plus your constant 4455. And if you were to graph that function, it would give you a pretty close representation of what we had for our population. So another thing to look at is that r squared value. The closer this value is to 1, the better your fit. So we got 0.893, which isn't that far. It's not a perfect correlation, but it's not that far from 1. So we can actually go ahead and put that into our graph here. One trick to do that is if we were to, whenever we calculated that, so if we go to calculate cubic regression, we can say L1, comma, L2, comma, and then if we go into our variables, over to y variables, function, y1, and then hit enter, what that'll do for us is it'll put that whole function I just talked to you about, it puts that whole function into your y1, and you can go back to zoom 9 and notice it graphs the line for you. It's a very good fit. Notice some points aren't quite on the line, but it does the best that it can to match your data to that function. So for our final answer for that, we would just write that function that we put in our y1. So what I did is I copied that function down and rounded some numbers off so it looks a little bit better. The last thing that we want to do is figure out what would the population be estimated in the year 2012. So we don't want to put 2012 in for x because remember we were using shorthand for the years. So instead of 2012 we're just going to put f of 12. And if I were to go ahead and put that into my calculator. If I put 10.02 times 12 cubed minus 176.3 times 12 squared plus 807.5 times 12 plus 4455, I should get a value of around 6,069, which is a rough estimate of what the population would be in the year 2012. Now, if we wanted to, we could actually take a shortcut and use our graph up here to figure out the value of what this function would be at x equals 12. So if we go to second trace, which will calculate our value of x equals 12, notice we at first get an error screen because what happened was our window was not valid for 12. We don't have 12 over here. So what we'll have to do is we'll have to change our window. Let's make our x min, we can keep that at 0.3, but let's make our x max at maybe 20 and regraph it. So you can see I kind of squeezed my data into that point, and that's what my function looks like. So now if I try to find my value of x equals 12, notice I get y equals 6,069. So that's a much quicker way of doing it than typing that whole thing into your calculator. And I know I said that was the last thing, but there is one more thing we want to find, is what year will it be when the population equals 10,712. So a trick we can do to use that, because it wouldn't be very fun to really put that in here and factor it out and figure out the answer that way. What we can do is we can graph a second line. So let's go into my y equals. Let's graph a horizontal line at 10,712. So when we look at both of those on our graph, let's see if it'll, might have to go to zoom fit. So there's our first graph and there's our second graph. Notice that 10,712 is way up here where my graph climbs up there. So it's probably going to be a year quite a bit in the future. What we can do, we can go back to that calc menu, go down to number 5, which is intersect, and we can tell it our first curve and our second curve, and the guess would be where I move my point. So maybe about right there. Helps the calculator out a little bit so we're not waiting forever. And it looks like my intersection is at 2014.9, so right about the beginning of the year 2015 seems to be where that population is going to hit 10,712. So one last thing I would like to try an example. I would like you to try an example on your own. And I know that's a lot to remember with the calculator, but I would like you to try this to get some practice, you know, making a scatter plot of this data, figuring out a line to match it, and then go ahead and figure out the number of fruit flies that would have hatched after 8 days. And once you figure out the answer to that, that concludes today's lesson. Let me know if you have any questions on either the lesson or the homework, and good luck.